Hello, everyone. Thank you for joining us today for our 7th webinar through the Canadian Underground Infrastructure Innovation Centre Academy. Today's webinar is titled Dewatering and Trenchless Construction and will be presented by Stephen Biase. Stephen is a senior hydrogeologist and project manager with Stantec Consulting. He has 23 years of hydrogeological consulting experience and also spent 4 years as a dewatering contractor who was responsible for estimation and design of construction dewatering systems. His experience includes construction of subway stations, tunnels, mines, and deep foundations.
Thanks for the introduction. I'll just preface this chat by saying that dewatering means and methods are they're designed for local experiences. All dewatering is regional in response to the local soil conditions. So the slides that we're going to flip through are generally the Greater Toronto Area experience, Southern Ontario, and so that's what you're going to be seeing as we look through these slides. When dewatering works well, it's a really beautiful thing. With respect to trenchless installations, usually open cuts are still required for the shafts, for the launch and recovery shafts. And so, as you could see in the attached, this was a launch shaft for a subway tunnel. And when dewatering is working well, everything seems to jive, and projects move along swiftly. As Carl Terzaghi said, if in a world without water, there's no need for soil mechanics, and excavations are very simple. So unfortunately, in our world with lots of water, things can go wrong. This launch shaft actually had a dewatering system. It just wasn't operating as expected. And as Hugh Golder once said, design of a dewatering system is no job for an optimist. And if it worked most of the time, I'd probably still be in that business, but it can be a very treacherous path when things go wrong. As dewatering systems don't perform, soils will slough, and as excavations get deeper, voids occur on the outside of the shoring. Cranes can no longer be mounted on the outside because of stability issues. Neighbors usually call, talking about cracks in their foundations, and everything goes wrong. And so generally in our experience with the dewatering, there's generally common headaches that tend to occur. And so just a few of them here that these are the normal ones. When you have a large excavation up here on the left and you have shoring interfaces, so when you're going from caisson walls to pile and lagging walls, generally along those interfaces, unless your dewatering system wraps around very well, you'll find seepage of water where you didn't expect. Or over on the right side here, if you have soil interfaces where generally you have a silty soil and then a thin gravel layer, water is going to follow path of least resistance, and it will find its way into ruining your sidewalls and causing a mess in your excavations. Same thing, if your excavation is going to encounter bedrock, you're always going to have, even the best dewatering systems won't be able to capture water slipping along the interface between the soil and the bedrock. So these are challenges that usually occur. Some example videos you can see here.
This has gotten worse and worse as we're going.
Yeah, it's gonna keep getting worse.
This has gotten worse and worse as we're going.
Yeah, it's gonna keep getting worse.
This has gotten worse and worse as we're going.
Yeah, it's gonna keep getting worse.
Other issues. Going back to our slides, while dewatering methods haven't really changed in the last 40, 50 years, advances in tunneling definitely have. And so I can remember 30 years ago, dewatering systems were always used to support tunnel shafts and for basically for caisson pile installations and for large wet wells. dewatering contractors were always used then. And I remember when to the Greater Toronto area, when tunneling contractors started coming in more, especially when Ward and Burke came in, with Keishon shaft construction, it seemed like dewatering, they really allowed dewatering wouldn't be used anymore for the purpose of construction. And so now now it's pretty rare. Dewatering is only used for large open cuts, as the tunneling contractors have advanced so much and they provide so much more confidence in meeting construction schedules. And so the one thing I can tell you, just based on our experience here, if you have an option where you're going to have a trenchless installation where basically shafts can be constructed by the tunneling contractors, even if it's a lot more expensive, you take it and let them do it. And if you get a cheaper option of having dewatering contractors come in and you do some sort of open cut to support, I promise you're going to pay for it later in times of cost, schedule, and heart attacks. And so, especially where you got issues of, where groundwater quality issues are known, if you got sensitive water features nearby, soils, limited space, these things can kill a dewatering system. And so generally, just to go over, whether it's trenchless or open cut, the approaches to dewatering, they're generally the same. What you're looking at here is it's basically a plot that we use to figure out what approach we want to be taking. So on the y-axis here, you'll see the depth of excavation, or the amount of lift, of how much water you have to lift, or essentially the depth below grade you have to draw your water table down to. And on the x-axis, you have your soil hydraulic conductivity. And so for shallow excavations up at the top of the page, sump pumping is generally used, and these are the cheapest form, and they're widely used and generally very successful. As you go deeper to anywhere between 5 and 9 meter depth, you can use a single stage or double stage well points. Well points are usually $1,000 per well for installation, and you're going to need them at 2 to 3 meter spacings wrapped right around your area of excavation. Once you start going deeper, it really depends on how transmissive your soil are. If you're in a silt or clay or loamy soils, adductor wells are very effective. They're $3,000 a well and also required pretty much 2 to 3 meter spacings around your excavation. Where you're lucky enough to have sand and gravel soils, the groundwater can be managed with classic groundwater wells of 6-inch diameter, and to the tune of 16 to 24K per well, depending on how deep they are and how sophisticated their design is. And so this pretty much tells us what our approach is going to be. I'm just going to talk briefly about the well points and the adductor wells, just so you get an idea of what's involved with them and how they're managed, as sumps and deep wells are more commonly understood. So well points is basically you'll have a vacuum. They're a vacuum-based well system where you'll have a vacuum pump, and that'll be connected to a header piping. And the header piping will be connected to a series of wells. All wells, they're generally going to be 7 meter deep. They can only lift water at the well themselves a total height of 6 meters. It's a matter of partial pressures. The best vacuum pumps in the world can't do better than that. And so generally what we do is the wells are spaced at least about 1.5 meters off your excavation top of slope. And generally what you try and do is you can expect at a distance of about 15 meters laterally from a well point, you can get at least 4.5 meters drawdown. And so that usually, when you double side your well points, it usually works out for the larger excavations. And so this is a typical well point system approach. Well points, they're generally 1.5 inch to 4-inch diameter, depending on how much water you need to move. The well constructions are PVC. You can get 15 to 40 gallons a minute out of each well point, depending on your formation. And the well screens, they have to stay at least 2.5 meters below grade. Otherwise, if they get close to surface, they are going to lose their vacuum because they're so close to atmosphere. So there is it has to be the well point depths. It's usually between 7 meters and 3.5 meters. They're ideally where you want to be placing them. The construction of well points, I'm just going to clip to a video so you understand. The construction of well points is pretty much all the same. What we do is we through the yellow line, and the well point is installed. After the well point is installed, then what and basically and then it's a process of cleaning up the well. As the well is cleaned up by just agitating crews will get 30 wells installed in a day. And for a 200-meter system, you're generally looking at for a 200-meter system, you're generally looking at about 75 wells to be installed in total. So some of the figures here, you're looking at the well point pumps and wells installed in tunnels. Well point pumps they're very good. They can usually pump depending on what your needs. There are different types of pumps. My favorite are the ones that are versatile, that can manage low flow and high flow conditions. And so one of the pumps you're looking at here is what we call a double pump. It's a large tank. Water gets sucked into the tank. Once the tank is full, a second pump pushes the water out of the tank and more water keeps coming in. And so whether your formation is a low flow or a high flow, pumps like this can manage it. And so they give you peace of mind that the pump won't burn out if for example, like a piston pump, which is used to nice steady flow rates that never change. Those aren't as applicable as some of the other ones that can manage all sorts of conditions. So well points can only operate on about a 200-meter long system. After that, the system becomes too long to maintain the partial pressures to keep the vacuum. Rental prices for a 200-meter system is generally about $450 a day per 200-meter system and pump. Right? And on a per meter cost, it's generally about $300 per meter length of a well point system. In tunnels, we use well points in tunnels. Basically, if a tunnel is created and they want to build a subway station from the tunnel out, what they'll use is the same type of drilling rig that installs the tiebacks on a shoring wall will be used to install well points outside, and they'll drill through and install well points outside the tunnel and dewater from there. And that allows them to start breaking down walls and building stations from the tunnel out. And so in these pictures here, what you're seeing is changes or modifications to existing tunnels where they have to break the tunnel bottom. And so well points were installed, and it's a pain because they have contractors to work around the well points, but it was the easiest way to carry on construction after rupturing the bottom of the tunnel. Adductors are a double pump system. A double header line is what we call for an adductor system. Now, these types of wells-based dewatering systems are used for much greater depths, and so you're going to have a recirculation tank, and you'll have two header pipes. One is a pressure line, and one is a return line. And so you can see on here, you'll have your adductor well, which is a 2-inch well. Inside the 2-inch well, there is a 1.25-inch, what we call below ground assembly. So on this figure, you can see the purple pipe reflects the 2-inch well, and the brown pipe reflects the 1.25-inch below ground assembly. There's a venturi tube you can see at the bottom, identified by this square, and a leather packer expansion point. And so basically what happens here is water is pushed down between the 1.25-inch and 2-inch pipe. Once it hits the leather packer, it bounces back and goes up the venturi and returns through the 1.25-inch line. And when it does that, it does it at such a velocity that formation waters below the packer get sucked in. And so this is how an adductor system operates, where you have a pressure line that pushes the water down, the return line that receives the water back. The pressure line, because of there's limited diameter available, the adductor wells can only capture about 10 US GPM. And so often you might have to tighten your spacings or need additional wells. They're generally designed for the low flow zones, but you still might have to tighten your spacings a little bit just because of the limited yield of the adductor systems. So this here is a picture of the tank. And so just a reminder, so the tank represents a reservoir. So the water that is fed into the pressure line and the water that returns from the return line, it both goes to a tank, to the same tank, but there's an overflow. So the new water that's brought in from the formation is allowed to overflow and discharge. But you always need to keep a certain amount of water in the tank for the system to operate. And so the prices of these systems, it's generally about like $950 a meter for installation, and it's somewhere between $1,000, could get up to $1,500 a day for rental of the system for a 200-meter system. Generally takes 2 to 3 weeks to install, depending on how deep the adductor wells are. And the real headache with adductor system is that it's much more maintenance intensive than any other system. The other thing is, if you have poor impacted groundwater quality, if you have high iron or sulfates or manganese, these will quickly destroy an adductor system. And so I never suggest using such systems where you know that you have impacted groundwater quality. So an example here, job in Toronto, where basically you're looking at a video. The filled with a chemical precipitant, and you can see the water starts flowing again once it's cleared. So that happened to be a job where they tunneled 90% of the project. They left 10% for open cut with adductors supporting the dewatering, and that 10% turned out to be the disaster and caused more problems than anywhere else on the site. And so again, if you're tunneling most of the area, stick with the tunneling, especially when you know you have groundwater quality problems. And just a brief mention on deep wells. Deep wells are where you have, these are usually 6-inch to 8-inch diameter wells where you have submersible turbine pumps in each well, and basically they all lift water up to a header pipe and discharge off a tank. So this is more simple, classic dewatering. The wells are much more expensive because they require a specific screen design, and so generally you're looking at pricing. Generally, you're looking at pricing overall about $24,000 per well. These are Canadian dollars, by the way. And rental prices for the system, those are usually cheaper, generally in the neighborhood of $50 a day for 200 meters of system. Most importantly, for the engineers here who are responsible for providing specs, best thing you could possibly do is have appropriate level of characterization. And so a decent amount of boreholes, a good understanding of the geology. You want to have boreholes that go at least 3 meters below the depth of your excavations. And the reason for that is that's usually where the well screens would ideally be placed. I'm not a big fan of pumping tests for every single situation, but a lot of soil grain size analysis from around the screened area is enormously helpful in trying to figure out just what your flow rates can be expected to be. Also, good understanding of the groundwater quality is really important as well. So helpful recommendations you're going to want to include in your report, aside from your standard assessment of ground conditions, basically commenting on how hard these soils are, if they're going to hold their form, how quickly they can be expected to slough, if it's immediately upon excavation or if there's some time. Basically, how transmissive the soils are. How long do these excavations expect to be open for? Do you need standby and backup systems? What is the water quality? Absolutely, what is the elevation the water level needs to be drawn down to? Flow rate is never a performance target because that'll vary. It's always got to be what is the elevation target for the dewatering. And something I always mention is basically when you're in a lot of contract specs, you're going to have those owners or engineers that will sort of deflect all liability, as you might see in the top. You'll see a lot of exculpatory language in some specs where whatever the geotechnical reporting indicates, the accuracy of it can't be confirmed, or there's no reliability on it at all. I'm not sure why that language. There's some municipalities that push that sort of language. I've always found that projects go much more smoothly with contract specs that you see on the bottom here, where basically a GBR, a geotechnical baseline report, has been prepared, and an assessment has been done, and a baseline of soil conditions has been identified, and that reflects the baseline from where claims can be judged later on change of ground conditions. And so usually when there's like a sharing of risk or an identification that change conditions could be reflected and a baseline report is provided, that's when things usually go better. So thank you very much for sitting through this presentation. I don't know how far I'm over, but I can take a look for any questions if anyone has any. Okay. Sure. Okay. Questions popping up. Can the initial geotechnical report be considered the baseline? Baseline reports, at least in our area, they mean something. It's a little bit different from a design report or a standard geotechnical report. In the baseline report, there is effort that specifies the range of a certain parameters that can be expected. So for example, how transmissive the soil is, the hydraulic conductivity, will specify a lower limit, an upper limit, and what can be expected. And the same thing can be expected, can be provided for the types of soils that are to be encountered. So I haven't been through a lot of legal proceedings. I've dealt with a few dispute resolutions, but Usually a baseline report is a special entity where it's all parties recognize that it's it's in fact the baseline, as opposed to a standard geotechnical report where it's just sort of issued and sometimes contractors are getting it after the fact. One thing I'm going to go back to is the Venturi tubes, in case they missed it. So again, for adductor wells, we have a 2-inch pipe that were installed. So the video that was showing the installation, you have a 2-inch pipe surrounded with gravel pack. The 2-inch pipe has a screen below it. Inside that 2-inch pipe, there's the 1.25-inch pipe that's installed, and this is what we call the below ground assembly, which it's installed at the bottom of every 2-inch pipe, and the bottom of this below ground assembly sits just above the screen. And again, so what happens is water is from the pressure line and the above ground assembly at surface, water is pushed down between the 1.25-inch and the 2-inch pipe. And then once it hits a leather packer at the bottom, it turns and goes back up through the Venturi and up the 1.25-inch. And generally you have 10 gallons a minute that's required to flow through the well from the pressure line. And an additional 10 gallons a minute capacity is available to be sucked up through the formation up into the Venturi, because the maximum that an 1.25-inch pipe can yield is about 20 gallons a minute. So just for any of those that missed it, I wanted to make sure that you were following on how these adductor systems worked. Oh, okay. You said gradation test, but any recommended test for cohesive soil? Speaking as a hydrogeologist, I'm mostly interested in a gradation test because it's from that I'm figuring out how much water is going to yield. How cohesive or the Atterbergs, it's not so much my area of expertise. Will we be able to have a copy of your presentation? Good question. Not sure. We'll have to follow up on that, especially because I've had some authors who graciously provided me materials and I have to get their okay. How effective is dewatering in lacustrine soils, low hydrogen? So in silt soils, it's let me put it this way: the finer your formation, the less effective your dewatering will be. Sandy soils, it'll work very well. As you get into silts, it will not be pretty. It will be a messy dig regardless. But the well points can take some edge off during construction, but you will still have to sump vigorously in the silt soils. In the clay soils, you're down to sumps. And this just follows on the basically our chart up here on how you want to be using your dewatering systems. So once you get into clay soils, you're in the sump pumping here. You're outside the range of well points or adductor wells. What are the main contractors in trenchless technology in Ontario? Just naming a few, and most of them have come in and changed, and they've changed over the years, and most of them have come in lately. So Dragados is doing a lot right now. Ward & Burke is always around. McNally's is around as well. These are some of the ones that generally they're in my experience. I'm sure if you just look up tunneling contractors in Ontario, you'll find quite a few. Dewatering can be done throughout the year or only construction season? Definitely throughout the year. The only issue is during the winter, you will have to winterize and heat your dewatering systems. How common are baseball reports used in contracts? I'm sorry, I'm not following on that one. The baseline report would be included with the tender documents in lieu of a standard geotechnical report. These will provide basis. Yes, this is a true statement. This is what I find here. Have you ever had zinc become an issue with regards to water quality, dewatering discharge, where it was previously not? water quality is a heck of a thing. You never know what's going to happen. Even if you have favorable results in the beginning, anything can happen with time. And that applies to zinc, manganese, iron, just about anything. And that's what makes it such a tenuous process. Is that there will be no dewatering and trenchless construction except the shafts. Yeah, that's pretty much the case, correct. What references do you like to use to correlate grain size performance? I'm a Hazen person myself. What dewatering would be affected by ambient temperature? No, never been an issue. And what's the best method to identify large sand seam and fine soils that may be missed? You know what? Drilling is the only way to identify what soils you're going to have, and is it possible to miss them? All the time. This is why we get surprises. This is why dewatering can be a real tenuous thing. What formula, if not Hazen, would you consider to be the best estimate in soil permeability K? Okay, so to be honest, generally why Hazen is so favored is because it's really that 10th percentile that drives how much water is flowing through a formation. And so just as a student, I was comparing using Hazen to a Mash and Denny or to some other approach. But I got to be honest with you, I just consistently found that Hazen works the best. And I came to realize that it's that 10 percentile drives everything when you're trying to figure out water flow. So for that reason, that's why I'm such a fan of Hazen. So thank you very much for everyone for taking part in this presentation. Hopefully you're all satisfied and I answered your questions well. Thank you.